Good morning, everyone. Today we're going to present an overview of the Geodatabase API in ArcGIS Pro. How's everyone doing? Pretty good? Good. It's the first time I've ever presented in this room. It's a little smaller, more intimate. I like it. Did everyone notice the gigantic diamond in the back? Thought that was a nice touch. Yeah. There's a bar as well. Excellent. Okay. So first, introductions. I'm Colin Zwicker. I'm the lead Geodatabase test. On my left, on your right, is Sree. He's the lead PE for the SDK. And on my right, your left, is Nghiep, and he's the lead developer for the SDK. So we'll be presenting this for you today. Okay, first, very quickly, some things that we will not be going into particularly deeply today. These are the add-in model in Pro, the threading model, or editing of features. There's a session today at 10 o'clock in Mesquite. If you're interested in editing features, I ask you to go to that. Okay? We're going to talk about core data access today. So what is the Geodatabase API in ArcGIS Pro? Well, it's a managed.NET API, which was built specifically for the purpose of extending the application. This is not the internals that ArcGIS Pro are built with. This is for extending the application in a convenient way, right? So we took a look at what we had. We had ArcObjects, and it was an extremely robust API. It was gigantic, in fact, right? Had a table class with 45 interfaces on them, each with 4 or 5 different properties or methods, right? And it was a little bit cumbersome and not particularly discoverable, right? You had to take that OMD around with you, and it was a huge thing, and it didn't work out so very well. So we took a step back and thought about this whole process again and said, what if we could make the API look what we wanted to, what would it look like? And this is what we're going to present today. So it's a little bit coarser grained than ArcObjects was. And it follows some of the models that the rest of the API does, the layer and the sim model. Like I said, it's the extensibility model for ArcGIS Pro. And in that way, you can extend the application in a looser coupling than you could with ArcObjects class extensions. So this API has been growing since 1.1 shipped. Each release, we've introduced more functionality. At 1.1, we supported the web geodatabase support level. This is simple tables, feature classes, subtypes, domains. At 2.2, we added versioning and feature service support. At 1.3, database access, query definitions, 1.4, joins, SQL syntax support, and feature services as a geodatabase. So the point here is that it wasn't all there at the very first release, and we're continuing to iterate on it and add as ArcGIS Pro grows. And we'll continue that. As they add new functionality, we will add new capabilities. So next, we'd like to ask Nghiep to talk a little bit about the architectural principles that we have for creating this API.
Good morning. The Geodatabase Managed SDK is a fine-grained API that allows third-party developers to write C# applications that work with geodata in ArcGIS Pro. It's engineered using industry-standard best practices for developing APIs and frameworks. That means it is object-oriented, it is strongly typed, and it is easy to use correctly and difficult to use incorrectly. In order to use this API correctly, you have to be aware of a key principle that governs Pro SDK with respect to how threads work in ArcGIS Pro, because ArcGIS Pro is a multi-threaded application. I'll talk more about this in a moment. Essentially, the Core.Data API is a facade through which ArcObjects functionality is exposed. It consists of 2 tiers. There's a managed tier and a native tier. The API is obviously implemented in C#. It interacts with the ArcObjects tier via a very thin interop layer written in C++. First and foremost, this API only supports DML or data manipulation language only operations. It does not support DDL operations or data definition language operations. What this means is that you cannot use this API to do things such as create a feature class or create Geodatabase. To do these kinds of operations that involve schema changes, you have to use Python. As an additive developer, you can use the geoprocessing library to invoke Python GP tools from within your add-in code. For example, in this code snippet, we use the geoprocessing module to execute the create feature class GP tool to create a feature class called named places in a file database called data.gdb. And the execute true async method simply returns a task, which is an IGP result, and you can inspect if it's failed, and et cetera, et cetera. From an application developer's point of view, the biggest difference between ArcGIS Desktop 10X and ArcGIS Pro API is probably the threading model. ArcGIS Desktop 10X is a single-threaded system. Its API is easy to use because your code simply calls into ArcObjects and it works. ArcGIS Pro, on the other hand, is a multi-threaded application. It matters which thread you use to invoke the Core.Data API. As far as an application developer is concerned, there are two threads you need to be aware of, even though there are many threads in the system. The first thread is the user interface thread, or the UI thread. The second one is the main sim thread. The user interface thread is a thread that basically you can do anything that has to do with the user interface. For example, adding a layer to the map. The main sim thread, you can think of the main sim thread as the thread that pretty much does everything, all the back-end stuff. For example, querying a database, connecting to Geodatabase, etc. That's why it's called the worker thread as well. The vast majority of the methods in this API are designed to run on the main sim thread. The primary mechanism that allows you to call into these methods that run on main sim thread is via one of the overloaded run methods in a static queue task class. This API strictly enforces the threading requirement. If you invoke any of these methods on the wrong thread, you'll get either a constructed on wrong thread exception or called on wrong thread exception. In this code snippet, we are in the UI thread. We call into the Geodatabase class to connect to a Geodatabase via the main sim thread. And the queue task.run allows you to do that. Now, if you're not sure if the method must run on the main sim thread, all you need to do is hover your mouse over the method in Visual Studio. You'll see a comment, this method must run on the MCT, use queue task.run. MCT stands for main sim thread.
Thanks, Nghiep. So, should turn my mic back on. Thank you, Nghiep. Now we're going to run through what some of the core classes are in the Core.Data namespace. So let's start at the very start. The data store is the container for your spatial and non-spatial data in this API. We have an abstract class that contains some of the common methods across them. And then there's more specific classes like a Geodatabase, which contain the bulk of the interaction for that data store. There's a couple different ways you can connect to them. You can use connection properties, a URI, or you can ask a data set that's already open for its data store. One of the changes we made in the Core.Data access of a data store is that instead of asking you, the developer, to generate a property set with a set of completely undiscoverable strings, we've created constructors, right? And these constructors can be fine-tuned by us to give you exactly the properties that are required to connect to that data store. So this is just a sampling of the ones that we have currently. This will, as I said, continue to grow as we support more data stores in the API. So the next data set I'd like to talk about is a table. Tables contain 0 or more rows. They support search and select, and there's a couple different ways that we can open these tables, right? This is the core of your data. You can use a Geodatabase data store to open data set, giving it the table type and saying open table name, right, this table. Or from a layer you can get the table, or from a row you can get the table. So the table contains the ability to create rows, to get its definition, to ask if it's a join table, to search and select, right? So this is the very core of the Geodatabase data model. Tables are inherited from by feature classes, right? Feature classes are basically tables with shapes, and they also support spatial queries or spatial selections, right? In a very similar fashion, you can ask the data store to open data set of type feature class and open a feature class. You can also say if the table is a feature class, then you can cast the get table from a layer as a feature class. And if the row is of a type feature, then the table you get back is actually a feature class, right? Conversely, you can ask to open a feature class as a table, right? So they go back and forth there, right? It inherits from table. The container for feature classes is a feature data set, and it's the collection of related data by a common coordinate system. And it's mainly used to organize classes and to constrain them for the use with controller data sets like topologies or network data sets or terrain data sets. It's a very similar model. You'll notice that this is a pattern we've used instead of having an open feature data set interface, right? We just have one style that we come back to, generic open data set of type, and pass back. You can do it. The next thing I'd like to talk about is relationships classes. These are objects which relate to tables or a feature class in a table within a geodatabase, and they're stored in the geodatabase. You can access the origin and destination feature class, or classes that participate in it from the relationship class definition, and you can also ask what cardinality it has. The relationship classes in this model come in two types. There is the relationship class, and this is maybe a sort of in-memory thing. We store the definition in the geodatabase, but there's no actual physical object in the geodatabase that models it. Or there's a attributed relationship class, and this is a relationship in which the user has defined some attributes on that relationship. Like if you think about parcels and owners, maybe the percentage of ownership is on the relationship between those two things. This type of relationship class attributed has a physical table in the database that backs it. The next thing I'd like to talk about is definitions. So in the ArcGIS Pro's Geodatabase API, we have data sets, which are the open object, and we have definitions of those data sets. And the definition is where we store the information about those data sets. So things like, what are the fields in the data set? Or does the table support global IDs? We've separated these two things to make them, to give a way to make it lightweight and discoverable, right? Instead of opening the entire class, you can ask for the definition, or you can ask for the definitions from the data store, right? And then you don't take the hit of opening a cursor and opening the table for every single time, right? It's much more lightweight. So from the different data sets, you can get the definition, like table.get definition. You can also ask the Geodatabase for a specific name definition if you're seeing if it's there, or you can ask for all of the definitions in the data store. And now let's have Sree to show us some of this.
Hello, everyone. Just go back to this. So I have a simple demo. It just gets the data store. So let's say I have this is an SDE file which points to an enterprise Geodatabase. And here each one of these is a data store type, like file Geodatabase, service, enterprise database, SQLite, shapefile. So right now this is an enterprise Geodatabase, and the load data right now would hit this method, the command, which would open the data store. So if you observe here, the data store is actually type of ArcGIS.Core.Data .data So all of the different data stores are represented here, going back to the method. So if it's a file Geodatabase, it's a file Geodatabase connection path passed to a file Geodatabase class. The constructor, if it's an enterprise, it's a database connection file, since we're using the enterprise, the SDE file here. If it's a connection properties, it would be a database connection properties object. For the service Geodatabase, which is for feature services, it would be a service connection properties. Again, a database connection file, even if it's a like a database which doesn't have a Geodatabase schema. SQLite connection path for SQLite databases, and finally shapefile connection path for shapefiles. And each of these are assignable to a data store reference. So once we do the load data, it shows up. So right now this would be a different type of class. So let's say I say feature class. What this command does is it goes over to the command which opens up the definitions. So this is what Colin was mentioning. So we want just to look at what definitions, like what data sets are there and what their properties are. And we don't need to open a data set for that. So we would just get the definitions. And as Nghiep was mentioning, most of the methods are have to be run on the main sim thread. But the get definitions is one of the methods which does not have to be. So because you see that I don't have a queue_task.run, which means that I'm running this on the UI thread. So if it's a Geodatabase, I'm casting it to a Geodatabase, getting the definitions based on whatever the dataset type I have selected in the UI, and populating the definitions. If it's a database, it's a little different. There's no way of discovering all the tables that are there, but we do get the table names, and then for each table name, you can get the query description and pass the query description to the get definition method on the database. And from that, you can get the definition for it. If it's a shapefile, it's the same. We don't have a way of discovering all the shapefiles given a directory. So the way I'm doing it here is that we get all the files in the directory from the shapefile connection path, and then for all the start.shp files, I send the name of the SHP file to get the definition. So either to get the feature class definition or the table definition. In this case, it's a DBF file. So the get definition method is existing on all of the data stores, but in different ways. And the next thing is, once you get the definition, so let's say I have selected, say, copy features here. You can see it populates all the properties with the indexes, the subtypes. This doesn't have subtypes, so let's see if okay. Yeah, so here you can see the subtypes that are there, the indexes. So all of these we are getting from the definition. We don't have to even open the feature class for it. So if, for example, if it's a table definition, we get the definition and all the details. The get methods will give you the alias name, created field, subtype fields, the model name, the subtypes, indexes, and so on. So yeah, this is like a simple demonstration of it. All of these samples are available on, will be available on the community samples, the GitHub repository. So yeah, back to Colin. Yeah.
Thanks, Sree. So the next thing I'd like to talk about is how we query data. And I said on the table class there was two ways. There are selections and search. And selections are a list of object IDs, and it's a lightweight way to highlight features on a map. They also have the ability to combine multiple selection sets together. All right. Search is a way to return rows via a row cursor. Right? And this style of cursor is table bound, meaning those rows know what table they came from. Our search cursor supports recycling as well. So how do we limit the number of rows that come back? And we do that through a query filter. Each of those select and search operations accept a query filter as a way to minimize the rows that come back. We can set the where clause or restrict the number of fields that are populated when they're returned via subfields. They also support the idea of pre- and postfix clauses, distinct or order bys, for example. Query filters are an exception to the MTC rule as well. They can be created on a non-MTC thread. Query filter is extended by spatial filter. So if you wanted to add a spatial aspect to it, then you could define the spatial filter. So a special type of cursor is a query def cursor, right? A query def cursor is available from file and enterprise geodatabases. They are not available with feature services. You have to give it the tables that you want to work on, and this could be a single table or multiple tables within the same data store. So you can think of this as a way to do joins if you want to, right? You could construct the SQL which would join two tables. Rows returned from query def cursors via the geodatabase.evaluate are not table bound, right? We can't guarantee that the SQL you've constructed is a single table, so we don't know what table to return. So it's a key difference between search cursors and query def. Couple little things. The query def description that you set up does not support field aliases. And if the tables that you have involved in the join contain more than a single shape column, it's always the leftmost shape column that gets taken as the feature class piece. And yeah, as I said, geodatabase.evaluate, and you can return a query def. So the query def is really good for a one-off query, but what if you want to use that more than once, say as a layer or input to a geoprocessing tool? We've given you the query table operation here to do that. It's read-only, and it's a virtual table, but it is a more efficient way to use that query def than continuously reconstructing it each time. From the geodatabase, you can call open query table, passing it a query table description. The query table description needs a few key things, though. It needs the name, it needs the query def, what am I going to query, as well as the key fields, object ID and shape. Okay, now let's take a look at working with some of these things.
Okay, so this demo is just for, this is already an existing sample, and this is for showing how we can work with spatial query filters and query filters. Here we have a feature class, crimes, and this is like a simple, a single class, like where you can say where major offense type is something or neighborhood is something. So let me just say Cathedral Park, and let's do a search. So this is the code where from the feature layer. So one of the ways we demonstrated earlier was getting the table definition or table from a Geodatabase by opening it given a path or given a file. Here from the layer, which is the selected layer, you can get the table, and then from the table we are looking at whether the map selection, is there anything selected on the map. So if there isn't anything selected on the map, we don't need to look at the spatial part of it. So we would come to the query filter where the where clause is simple neighborhood is equal to Cathedral Park. And once the query filter is specified, we would do a table.search, and once you do the row cursor, before you do the row cursor.move next, the current is null. So once it's just the row cursor is the normal enumerator, where until you do a move next, the current is not set, and you can keep on doing a move next until current becomes null, or move next will become false. And when you do a row cursor.current, the current is either a row or a feature. It is the reference that is returned is a row, but you can cast it to a feature. And depending upon whether it's a feature class or a table, it would be a feature or a row respectively. And there are two indexes on the row. One is the string-based indexer, and the other one is the integer-based indexer. The string-based is where you can pass in the field name and you can get the object and then cast it to wherever you need. So in this case, if I just say F5, remove the breakpoint here. So it gives you back 227 rows. Now I want to just select like a part of the selection and say I want to see the same result in this small part of it. If I do that now, because the map selection exists, the way we are doing it here is that the selection is a core.data.selection. And on the selection you can do a search. So let's say you had the object IDs 0, 1, and 2 in your selection. The search would return you the rows for those IDs in the selection. And the same thing goes for the row cursor. But what's interesting here is that you can get the shape from the feature. You see the cast here to the feature. And once you get the shape, you can union this with all the features that are returned, and the envelope that you get at the end of it is the extent of all the features that are selected in the map. So once you get that, you can use the spatial query filter. And the spatial query filter, you can create an envelope builder, specify the filter geometry. The spatial relationship is contains. We want all the features that are contained in this filter geometry. And then you also have the where clause, which is neighborhood is Cathedral Park. So you do this, you'll get like a lesser number of rows in that, and you can look at the result here.
There's a question over here.
Yeah, just wondered, it looks like it's just a I enumerator instead of I enumerable, so it can't do for you on it.
It doesn't actually implement the interface, it's just modeled that way.
Just model that.
Yeah.
Okay.
Yeah. Yeah.
Second question.
When working with cursors, you just need to wrap it in a using. You don't need to do anything besides that.
No,
you guys
nothing.
Are doing all the releaser stuff on
Yeah.
for us.
You don't need any of those things.
All right, so just a using.
Yeah.
Be
All right.
Good to go.
So the question was, do we have to do any work when we're working with the cursor beyond a using statement? And no. The answer is you can just use the using statement.
Yeah.
Did anyone attend the effective geodatabase programming earlier in the week? Did anyone notice something that Sree did that was in my top 10 don't do's?
Access the cursor's attribute name several times.
Yes, he did, didn't
Okay.
he? and I'm still calm and serene. I haven't freaked out.
Sorry, Colin.
It's okay, because one of the things that we optimized was that on the first call to that, we cache it on the back end. And so that it's okay to do that now. That's why that's why I'm still sitting here and not. Okay, let's keep going. That's pretty good, by the way, that you remembered that. I'm impressed. Okay, so the next thing I want to talk about is a helper class that we have, and that class helps us build syntax that's agnostic to the DBMS that we're executing the query on. This class is a SQL syntax class. And like it says, it uses the generation of SQL across multiple databases. Like, for instance, if you have a SQL clause where you want to make the string uppercased, then on some databases that's UCase, and on some other databases that's toUpper. And instead of having code in there that says, like, if I'm this database, do this, and if I'm that database, do that, you can use SQL syntax to ask the data store, hey, what is your toUpper function? And place that in your where clause when you generate it. Like I said, it's actually obtained from the data store itself, and it can be used to fully qualify a table name or a field name, or to return the owner of a table name, to find out what SQL functions are or are not supported on a database. It can allow you to find keywords, things that you cannot possibly call a field or a table in that database. And it's really useful when you're creating fields via geoprocessing, right? Before you create the string, you can ask this, is this a reserved keyword, or is this an invalid starting character for a table name? Next thing I'd like to talk about is joins. So at 1.4, we started to support joins, and they're used to combine fields from two tables into a single table representation. And we can support joining tables from a single database, so two tables from a single database, or tables across data stores with joins. So this is different than a query definition where the tables have to reside in the data store themselves. The join can be cross data store. So a file geodatabase table to a enterprise geodatabase table. They're created using a relationship class, and that relationship is either stored in the geodatabase as a physical object or is a virtual relationship class which you generate in your code. The results are read-only, but they do reflect the updates that happen underneath the table, so they're not static, right? We do not support many-to-many cardinality with joins. If you tried to do this with the in-memory virtual relationship class, it would raise an exception. So a join, you can say, once you've defined it with a join description, you can say join.getJoinTable. So for tables which are returned from a join that span multiple data stores, the definition of that table is not accessible. Okay? But if they're within a single data store, you can get the definition back from them. And we will make every attempt to push that join down to the database, right? So within a data store, two tables are joined, we'll push down to the database. But if we cross data stores, then we'll have to do the join client side. So it's something you want to think about. It's possible, but it will be more expensive. The virtual relationship class has a second use, and that's to support a relate of a table. So a relate two tables. And you can do this from the table by saying relate to and the table that you want to relate to and passing it the virtual relationship class description that you've built. So now a little bit about databases, not geodatabases, but just databases and how to access the layers in there. You actually saw a little bit of it in Sree's first demo. And this is through a concept we call query layers. So we can access these tables either from a table, like by passing the table itself, or by passing a SQL statement which we've generated. We can modify the query description to set the unique fields, which that unique field must not have any nulls in it. And the table must still must still adhere to the ArcGIS rules of what a table is, right? It can only have a single geometry column, for instance. And you can access that table by going to the database and saying dot open table, right? Passing it the query description. Well, we talked about several different ways that we can use the Geodatabase API to query the data. But what's the best way for each one? Well, we've tried to lay it out here, and you don't have to absorb all of this right now. You will get a copy of the slides later. They are available, so. But just let's run through a couple of them here. Say that you have a simple single table registered with a geodatabase, then call table.search to get the rows back, right? If you're doing a one-time query that might contain a join, then a query definition is where you want to go. If you don't like writing that SQL, use a join. If you want to reuse that query multiple times, then query table is your way to do that, right? If you want to pass that information into a geoprocessing tool, again, query table. What if you want to join multiple tables from the same data store? You can do that with a query def. But as soon as you cross data stores, it has to be a join. What about querying data from a simple database? Then we use a query layer. And how about if you wanted to join data in a database? Well, you are constructing the SQL, so feel free to construct a join in the SQL that you pass to us. Cross-database join, okay, we said that already. It's only possible with the join class. So let's take a look at what that looks like.
Okay, I'll try not to screw up this time. So this is like a simple add-in where we want to show you different join types. So this is just to have a join where I select a geodatabase or database or something like that. And let's start with both geodatabases. And let's see. Let me say counties, and I would select the state name and have the name, the object ID, the county fibs, and let me take the shape from the left table, and from the right table I'll take the states. I want to have a counties to states join, and also have the states, and I want the state fib, subregion, and state abbreviation. And this is one-to-one cardinality because each county has one state. And I would just give a layer name like counties to states, geodatabase. So I want to do a generate join. So what we're doing here is that I'm getting the left table and the right table for both of them. And if you observe, they are feature classes. And what I'm doing here is that if it's the same geodatabase, I'm doing a query table. If it's the same database, I'm doing a query layer, and otherwise I'm doing a join. So because it's the same geodatabase, I'm checking, is the connection string for the left table and the right table the same? If it's the same, then they come from the same database. So I'm getting all the fields now. The fields, I get the fields from the left table, what I've selected, and the right table, and making them into a comma separated list. So now I'm saying, are both geodatabases? Yes. So let's make a query table layer. So in the query table layer, I am generating the tables using the inner join or left outer join based on whatever you have selected. So let's do this. Let's look at how this looks. So we have counties inner join states on state name is equal to state name. Now, we set this to the query def tables. So there are two ways of doing this. One is you can say tables, you can set tables to be a comma separated list of tables, which is counties, comma states. And then in the where clause, you can say counties.state name is equal to states.state name. Or you can have a join query, what I'm doing here, and set that to the tables, and you wouldn't need to have a where clause. Or if you had a different where clause, you can add that to the where clause. So since I'm not doing anything specific but just doing a join here, I'm not going to set the where clause. And I'm setting the sub fields of the query def to that. And then we are getting a query table description from the query def. And I'm getting the geodatabase from the left table because both are the same. And then doing an open query table from the query table description. Once we do this, we can pass in the feature class to the create feature layer method on the layer factory instance. And I'm just adding to the active map. So when I do that, I should see that up there. And let's see the attribute table, how it looks like. So the attribute table, you can see there's object ID, the county's name, the state name, the county FIPS, the shape, the state names, state FIPS, subregion, abbreviation. So this is straightforward. So now let's see if we can do the same thing for a database. So this is a database and not a geodatabase. And let's see, let me say cities. I want to get the state FIPS. I don't have state FIPS here. So let's say I say state name again. I want to say object ID, shape. I want the city FIPS, city name. And from the counties here, I don't have a state names table, but I do have state names on the counties. So I say I want the state FIPS here. So it's again a one-to-one, and it's a query layer. So when I say generate joins, it's the same thing here, and we see that the connection strings are the same. And okay, right. So it's not a geodatabase, but it's a database. So we go in here and then say make a query layer. We get the fields, which is a comma separator list, and the join clause is very similar to whatever we had before, the inner join clause. And we create a query description from it, which is select fields from join clause, which is select whatever we have selected from the left table, join right table. Once we do this, as Colin was mentioning, we can do an open table with a query description. And this would give us a feature class or a table. So in this case, it's a feature class because it had a shape field. And we can do the same create feature using the same table. And we should see another layer here. Yeah, there it is. And you can look at the properties. It'll say query feature class. And if you look at the attribute table, it'll be a join with all of those when it opens. Okay, there it is. So you have the state FIPS, the state name, everything. So let's do an across database join. So from a database, I'm going to join to a file geodatabase table, the states here. So I'm going to say the same thing and say state name and a one-to-one. And let's do a left outer join this time. And then say counties to state join and say generate join. So okay. Okay. There's now a valid definition because I'm trying to get the definition out of it. Oh, it's because I have the other add-in which is expecting, okay, it's trying to get a definition out of it. Okay. Sorry for that. Okay, let's see. May quickly recover from that. Okay, so I'll just keep showing you the make join, how it looks like. The make join would have, you have a virtual relationship class description, which has the left field and right field and the relationship cardinality that we have specified. And this is where the relate comes into play. We are always creating a relate between the left table related to the right table through this relationship class description. And then we are doing a join description forward. You can do either a forward or a backward here. And then it can either be a left outer join or an inner join. And you have the target fields. There are more fields here, like for example, you have the join type, which we already talked about. We have query filter, so you can say, give me a join with only which matches the query filter, and also a selection if you need. Let's see, let's give us one last try and make sure this works. Okay. That's why. Sure, join stop being. Was doing counties to states. Okay, I am the UI developer sometimes. Okay, finally. Really? Okay. So 1-to-1 and some layer. So if I say generate join now. Okay, let's go into the join code here. 5.11. So you have the virtual relationship class description, the join description, and the join type is inner join because I didn't click the field. You create a new join out of the join description. You get the join table, and if the join table is a feature class, because if it could be not a feature class, you would create a feature layer out of it. Let's hope it doesn't. Okay. Yeah, the other, I have to uninstall the other add-in. Sorry.
It's okay.
Yeah. Sorry about that.
Thank you. Oh, we have another question over here.
What exactly is a forward join? I totally know what inner and outer joins are, left and right.
So the question is, what is a forward join?
Okay, so let's say you have a left to the right table, right? A forward join is where you're joining from the left to the right. So when you do a backward join, it's saying that you're joining from, let's say when you say the cardinality is 1 to many. So the 1 is from the left to the right, so yeah.
It's the cardinal, it has to map the cardinality.
Yeah, exactly.
Correct. Okay, let's keep going. So a couple little things. We also have versioning support in the Pro API, and this is retrieved from the Geodatabase if versioning supported is true. And you can get the version manager, and from the version manager you can connect to a moment, you can get all the current versions, you can get the historic versions. And we also support getting differences between tables. So you can ask the table for its differences. Here's my one slide on editing. It says use the editor. There's a session in Mesquite C today at 10 a.m. if you'd like to go take a look at that or review the slides when you get home. Core host. Okay, so this is a concept that allows our API to be executed outside of ArcGIS Pro. It's run in a headless mode. And in this mode, like if you want to do DDL, then the geoprocessing tool has to be fired by executing Python yourself, right? It doesn't have the integration. Editing is not possible in this mode, right? Because ArcGIS.Desktop.editing is above us in the stack and is not available if the stack isn't there, right? It's headless. So we do give a way to apply edits. It's far more raw than the editing experience you get, but Geodatabase.apply edits, it is possible to make a modification in a headless application. Okay, let's. Did you say something?
I just want to like show you guys. So the simple thing is this is a console application. You just have to add the ArcGIS.Core and ArcGIS.Core host libraries to the references. The second thing is you need an SDA thread attribute because when it's running in headless mode, it expects this attribute to be there. The third thing is you have to have host.initialize. This is the core host, and when you do the initialize, it initializes your license. but make sure that you have signed in Pro as either as a concurrent license or as a named license, because that's required. Even though you do a host.initialize, that needs to be signed in. And once you do this, you should be able to just run it and be able to just work. And the fourth thing is also that it should be a 64-bit application. And as you see, you can just get the data out of it without having to start Pro. So I just want to show that. Back to you.
That's what happens when you kill an app. Okay, so best practices, don't kill your app. Let's start.
So now I'd like to discuss some of the best practices that you should be aware of when using this API. So even though there are many classes in this API that consume native geodatabase resources, as a third-party developer, you don't have to be concerned with objects not being disposed of properly, because C# is a managed language. During finalization, its runtime garbage collector will dispose of any object that consumes native resources. So you can rest assured there won't be any resource leak, as that lady alluded to earlier when she didn't see this complicated logging that you see in ArcGIS Desktop 10x. However, the garbage collector by its nature is deterministic, meaning we can't predict when the garbage collector will kick in and start finalizing dead objects. So if you have workflow that requires you to close a geodatabase at a precise moment in order to release logs, then you will have to either wrap the operation in a using statement or call dispose on the object in a finally block. So for instance, in this code snippet, we have two variables. The first one is feature class indeterministic. I open a geodatabase open data feature class, and assign to it. The second one is called feature class deterministic. I open this data set inside using statement. So the first one, when execution leaves the scope, leaves the block, the garbage collector will eventually kick in and clean up, dispose of the native resource. But exactly when that happens, we have no idea. It could happen the next second, next minute. We can predict when the runtime garbage collector will take over. On the other hand, the second one, as soon as the execution leaves the using statement, the API will clean up everything for you, will dispose of all the geodatabase logs and et cetera. So if you have workflows where you need to create temporary geodatabase to store temporary stuff, when you're done, you need to delete that temporary database first. Then this will give you full control over when that database is released. So over the next few slides, I'm going to talk about some of the best practices that you should follow. So do explicitly dispose of objects of the following types. Anything that's derived from ArcGIS.Core.Data, the data store. For example, Geodatabase. Geodatabase is roughly equivalent to workspace in 10x, desktop 10x. The second one you should explicitly dispose of via using statement or final block is dataset. Dataset is the abstract class, the base class for objects such as table, feature class, relationship class, feature dataset, etc. The third one is row cursor. You should definitely dispose of row cursor if you want full control over the lifetime of the logs and objects. Row buffer, and finally row and its derived type feature. So there are two standard ways in C# that you can explicitly dispose of objects. One is via the finally block. So I have a geodatabase and a feature class variable. In a try block, I do all this stuff. And when I'm done finally block, I just call dispose on it. So that's just when I dispose it. The second way is just use the using statement. This is simpler. the two forms you can use, the two styles. The first one, I can stack them up. The first one, using the Geodatabase. Right next to it, I just Geodatabase open data set, and that gives me a feature class. When I'm done, everything's cleaned up properly. Or if you don't want to stack them up, you can just use open braces, nest them together. Also, it's very easy to forget to dispose of the row cursor properly. In this code snippet, I want to count the number of rows in a table. So in this function, static function, my parameter, my argument is table. I do a search, I get a row cursor. So that's correct. I put a table, I wrap a table in a using statement. But then in the while loop, every time I do move next, I can move, I just increment a counter. When I'm done, just return a count. Here, I'm not explicitly disposing of the row, the feature that's encapsulated inside the row cursor. The proper way to do it would be like this. While I'm doing the loop, in the row cursor loop, move it next. After I do the counter, increase the counter, I should also dispose of the current, row cursor.current, which returns either row or feature. I call dispose on it. That ensures all the logs on the Geodatabase, on all tables, everything's taken care of when I'm done, when I leave this scope, the using statement scope. So the canonical form of processing row cursors is very simple. So I do all the using statements at the top as necessary, wrap on Geodatabase, table feature class, and I call search on the table, get my row cursor. While moving next, easiest to do is just wrap the current, the row or feature return from the current property in the using statement. And after that, you're done. You don't have to worry about anything. The last best practice is don't create static variable for classes derived from the ArcGIS.Core object base. The core object base is a base class in entire SDK, Pro SDK framework. The reason is if you declare a variable as static, when your add-in is first loaded by Pro, the thread that's responsible for initializing all these variables is a UI thread. Right away, you will get a construct and wrong thread exception. Remember, because all the Geodatabase objects, well, most of them have to be run on the main sim thread. So keep that in mind.
Thanks, Nghiep. So just a quick view of where we're headed after this release. In 2.0, that we'll be making some breaking changes, or at least they're allowed. So just a heads up if you're looking at the 1.4. Anything that's marked with deprecated, we'll probably remove. Okay. We are working, or I think we just installed last week, blob support for reading and writing blobs from a row. We're working on creating versions and deleting versions in the version management section, as well as annotation support. So that's a new thing that's coming with 2.0. We're going to try to keep pace with the pieces that are being added to the application. In a release after 2.0, some of the things that we're looking at are long transaction support and feature services, utility network support, topology features, dimension support, and WFS as a data store. So I'd like to say that here's two links for you to the conceptual help, the first one, and the community samples, and the demos that Sree gave will be on the community samples so that you can investigate those to your heart's content rather than flying by in an 8-minute demo. Two sections to point out on the conceptual help for this session, the Geodatabase section, as well as the editing section. Okay? Thank you guys very much for showing up on Friday morning.